or 6.5 and 6.6, what we are going to be focusing on here over actually the next 2 days is what we call a binomial random variable. So, I know it says binomial and geometric, crossing out geometric because that actually comes up in 6.7, and somehow I didn't correct this when revising some of these notes. So, but we will talk about geometric. But if we think about the word binomial, where have you seen the word binomial before in your math career? Okay, algebra 2, two numbers. What would you do with like those two numbers? Okay, instead of just numbers, could it be something else other than numbers when we're talking about a binomial?
Variables.
Okay, variables like x plus 4. That would be a binomial, wouldn't it? Because you have what? Two terms, okay, that you're adding together. If it's actually two numbers, you could simplify it or combine them and make it one. Hence, it wouldn't be necessarily a binomial. When we talk about binomial random variables, when you think of binomial, I want you to think of two probabilities. Okay. So what will happen is here today, first and foremost, is it's going to be unbelievably important for you to be able to determine whether something is actually a binomial random variable. So how you go about determining whether or not something is binomial or not is you have four things that you actually have to check. And I'm going to circle the first letters of each of these because it helps you remember. If you remember the acronym BINS, it'll help you remember the four things you need to check. The first thing that you need to check is it binary? Hence the whole idea of the bi in the binomial. Two outcomes. Okay? That's what the binary part is. You're only looking at two possibilities. Most of the time when you're doing the trials, you're either going to classify it as a success or a failure. I know this isn't the greatest example because I have two switches, but either the lights are off or the lights are on.
Success.
Okay? Success, failure. Or some of you might think that's success. So, okay? So you only have two options. Either you get a heads or you don't get a heads. Either you roll a 6 or you don't roll a 6. Okay? Those would be either you make the shot or you miss. Okay? Now, the next part is independent. Okay? They must be independent, meaning what happens on a previous outcome should not have any influence or impact of what happens on the next outcome. Okay? Knowing that I've flipped a coin 10 times in a row and got 10 heads in a row should not impact whether or not I'm going to get heads or tails on the next coin flip. Okay? Or knowing, okay, that I have, as you'll see in a problem later on, we'll talk about DVD players and Blu-ray players. Knowing that I own a DVD player and Blu-ray player should impact whether or not you own one. The third one is number, okay? The number of trials, that means how many times you're going to do it, okay, is fixed. Meaning you're going to flip the coin a set number of times. 5 times, 10 times. You're going to roll the dice 3 times. Okay? I'm going to sample 20 students. The last one is the probability of success. Needs to be the same for every single outcome, meaning that probability doesn't change. Okay? So if I'm rolling a die and getting a 6 always stays 1-6. But like if I'm looking at a deck of cards, I'm saying drawing a red card, if I don't put that card back, the probability changes. So therefore it doesn't become binomial. So the probability must be the same for each and every outcome. So one of the things you could be asked to do is determine, we'll jump down here to the examples, whether or not these samples or these examples here are binomial distributions or can be considered binomial. So we run through the binomial piece or the bins. So on the first one, it says roll a fair die 10 times and let x equal the number of sixes. Okay. Is it binary?
Yes.
Yeah. Yes. So either you get a 6 or you don't. It's either one or the other. There's only two possibilities. Is it independent? Boy. Yes. Okay. So yeah. Okay. I'll accept that. Dice do not have memories. Oops. IES. Really? Meaning what happens on one roll does not impact the next roll. Number. Are we rolling the dice a fixed number of times?
10 times.
Yeah, yes. Number of trials equals 10. Success. What's the probability of rolling a 6? For each and every roll. I forgot to write here, yes. So since the probability stays the same, are all four of these met?
Yes.
Yeah. So this is a binomial setting. So this would be something that we could, later on we'll show you how to calculate out these probabilities. Alright, second one. Shoots a basketball 20 times from various distances on the court. Let y be the number of shots made. Is this binary? Yeah. Yes. Either you make it or you don't. Either you make the shot or you don't. Is it independent? Does one shot influence the other?
Yes, no way.
Yeah. And I understand that there could be some gray area there. So we will say yes, but we're going to note assuming that one shot does not impact the next shot. However, I know that some of you that play basketball might argue that, wow, I start feeling a rhythm, okay, I'll start making more shots than missing. Or if I'm always missing, there is that psychological piece to it. We're going to, from a mathematical sense, kind of put that to the side. How about number?
Yes.
That's yes. We're doing 20 shots. Success. Is the probability of making a shot the same?
But if it says various distances.
It says various distances, doesn't it? So this would be no. The probability will vary due to the distance of the shot. So this one's a big fat no.
So close.
Came close, but that last one got us. All right, let's take a look at the third one. Observe the next 100 cars that go by, and let C equal the color. Is it binary?
No,
Why?
because there's multiple colors of cars.
No. Multiple colors of cars. So do I have to keep on going?
No.
No. I can stop here
Really?
and say no.
Perfect.
That's what I love about math. Once you show it's wrong for one of them, it can't be it. It's like true false. If I can find one counter example, okay, then I know the statement will be false. Okay? Now here's the interesting thing here. If I actually went through the rest of them, it would be at least independent because the color of one car shouldn't influence the color of the other. The number was 100 cars, yeah. The probability of success, assuming that there was an actual distribution of colors for cars, like in the United States, I suppose, but definitely not binary. If I were to change this and say let C equal a blue car, well, then maybe it would be. So now the question becomes, how can we go about calculating out these binomial or these probabilities once we get a setting? So if we go to the next page, we have this binomial probability. But I want to show you where it's coming from. Okay? So I'm going to give us a situation. I'm going to roll a die 3 times and count, or I should say, and count the number of 6s. Or I could just say I have 3 dice and I just roll them all at the same time and look at how many 6s I could get. What are my possible outcomes here? No, I'm rolling a die 3 times. Let me do it this way. X equals the number of 6s I get. Okay, 0 through 3. Because I could get 0 6s, 1 6, 2 6, or 3 6s. So now if I think about how I could calculate out those probabilities. If I think about 0, what has to happen on the 3 rolls? What has to happen on the first roll? You don't roll a 6. So no 6. What's the probability of not rolling a 6? 5 out of 6. How about on the second roll? No 6. And the third roll? Okay. So what would I do with those probabilities to get this answer? Well, I can't add them because it would add up to it would be 15 6, and that's over 1. You actually multiply them. Because it's like get a tree diagram. Okay? 6, no 6, 6, no 6. Then you do it again. So you're going to see there's a whole bunch of outcomes to take into account. So the probability of getting exactly no 6s is 125 out of 216. I apologize, getting no 6s. Did I say 5 6s? Or was I saying 5 6? Anyway, again, the probability of getting no 6s, rolling no 6s, is 125 out of 216. I'm going to jump to the last one here, because it's the easiest of the 3 remaining to calculate. This is getting all 6s. So this would be getting a 6, and a 6, and a 6. Okay? I know the problem already seems a little evil. So be it. I know. So each of those have a probability of 1 6 times 1 6 times 1 6. So 1 out of 216. Now I have the other 2 outcomes to figure out. This is getting one of them to be 6. So you might be thinking like this: 6, no 6, no 6. So that would be 1 6 times 5 6 times 5 6. When I do that, I get 25 out of 216. When I do this one, that's getting a 6, no 6. 1 6 times 1 6 times 5 6, which equals 5 out of 216. But notice how I haven't written them up in that top space yet. There's a reason why I didn't do that. Okay? What has to be true about these 4 probabilities?
They add up to 1.
They have to add up to 1, don't they? So if these were my answers, 125 plus 25 plus 5 plus 1, do those add up to 216? No, they don't. I've forgotten some of my outcomes. And here's the issue with just trying to calculate these ones that are in the middle, right? Meaning, between 1 and 2. On the outsides, they're pretty cut and dry. But when I look at this 6, no 6, no 6, okay, is this the only way I could have ordered it?
No.
Could have gone no 6, 6, no 6? Yeah. So that's another possibility. Likewise, no 6, no 6, 6 is yet another possibility. There are 3 different ways the 6 could have happened: on the first die, the second die, or the third die. So this probability has to be multiplied by 3. So this ends up being 75 out of 216. If I look at this one, notice how I get 2 6s and 1 no 6. This no 6 happened on the last roll. Could it have happened on the middle? Could it happen on the first? Okay, so there's also 3 ways I could have ordered that. So there's 15. Do all of those now add up to 216 out of 216? If I look at this, 75 and 15 is 90, plus 125 is 215, plus 1, 216 out of 216. Yeah.
Oh, never mind.
Why 3?
Just like 3 numbers?
Well, it depends on where the no 6 happens. It could have been on the last die, could have been on the middle die, so I'm like rearranging it, but it's a possibility, or it could have been on the first one.
So since it's on the third one?
So we did it on the third one, okay? No 6 on the third one, but it could have been no 6 on the second one.
So you could could have times by 2. No.
No, because it could have also been on the first one. Think about it like this. How many, if I look at my tree diagram up here, it's like doing 6, no 6, 6, no 6, 6, no 6, 6, no, 6, no, 6, no, 6, no. So what happens is, when I do all the 6s, that's what I got here. When I did all the no's, that's what I got here. But there's 3 ways I could get 1 6. And there's 3 ways I could get 2 6s. So I calculated out the probability of one of them and multiplied it by the number of ways. Okay? So what we've actually done here is this binomial formula, okay, which is given to you right here. This looks a whole heck of a lot more complicated than it actually is. But I want to define a couple things for you. First of all, okay, when we talk about n in this formula, n is the number of trials. K, sometimes we'll use the letter R. R and K are the exact same values. And I say that only because our calculator likes to use R. Our book likes to use K. But they go hand in hand. Okay? Is the number of successes you want. And P is the probability of success. Those are the 3 most important values you need to do a binomial setting. So if I think about this rolling of the dice problem, okay? If I'm looking at P of X equals, and I'm going to choose either 1 or 2. I'll choose 2 just to show you how the formula works. That's my K value. This NK in parentheses is actually the formula NCR, and that's where your calculator comes into play. You remember doing combinations back in Algebra 2?
Yes.
A little bit?
Yeah.
Okay. That's where you're doing combinations, permutations, factorials. Okay. Where order matters versus order doesn't matter. Well, in a binomial situation, the order doesn't matter. Okay? Because it doesn't matter if the 6 came first, if the 6 comes second, or the 6 comes third. You do count each of those, but okay, what we need to do is count the different ways it could occur. And this combination formula will do that for you. So like in our situation, what we were doing is we were rolling the die 3 times. We are choosing 2 of them to be 6s. So then what we would do is say, well, n or P to the K power. P was the probability of success, 1/6. We're raising it to the K power. K is the number of successes you want. We wanted 2 6s. 1 minus P. If P is 1/6, what's 1 minus it? 5/6, the probability of failure. So if P is the probability of success, 1 minus P you can think of as your probability of failure. We're raising that to the n minus K power. Well, if n is, in our case, 3, K is 2, how many does that leave us? Just 1. Okay. Notice up here, if I kind of scroll back up here for this one right here, notice how we're going. 1/6 times 1/6, 1/6 to the second power, 5/6 to the first power. This 3 choose 2, if you do that on your calculator, will actually be the number 3. Okay. So So one of the things I can actually do is on my calculator, is if I go 3, go to the math menu, over to probability, NCR 2, and then I could go 1 divided by 6. Whoops, raise it to the second power. So to the second power. And then I could times it by 5 divided by 6. Do I actually have to raise it to the first power? No. So if I hit enter, of course I'm going to get a decimal, but just to show you, math, fraction, 5/72. Uh-oh. Is that the same as 15 over 217?
Yeah.
Well, let's find out.
216.
Or 216, yes, thank you. Are they the same decimal? Yes. 5 over 72 is just reduced, because they both have a 3 in common.
So that is, you were just explaining essentially what the NCR does.
Yep. The NCR does, what it does is it counts for all the different ways you can order them.
Can we do it that way instead of writing it all out like that?
Yes. So, how we can start doing these problems by using this formula, I just wanted to show you specifically with how the formula works. The key things you want to identify is N, P, and K. So it says, here's a very basic example. Find the probability that a couple has 5 children that we're going to assume the probability of having a girl is 0.51. And I do that so we can decipher the difference between the probability of success and the probability of failure. So if I make it 0.5, well then the probability of failure and success are the same, so it's not as easy to see where these numbers sometimes go in the formula. So we want to know, again, exactly 2 of them are girls. So right away I go like this, 5 children. What value is that? What variable is that?
N.
That's N. Beautiful. What is 0.51? P. So now the K is going to come from these questions. So the first one says exactly 2 of them are girls. So I want to know what's the probability that X equals 2. So how the formula works. 5 NCR2. So I'm taking 5, I'm choosing 2 of them to be girls. The probability of a girl is 0.51. How many of them do I want to be girls? 2. So it goes to the second power. If the probability of a girl is 0.51, what's the probability of a boy? That will be raised to the, how many boys then do I need? 3. If 2 are girls, then the remaining 3 have to be boys. Yes, Taylor.
So did you do probability of X equals 2 because you want them to have 2 girls?
We are asked to find the probability that exactly 2 of them are girls.
And for these problems, we will always be given what the probability of one of them is. And
Yep. You have to be given N, P, and K. You have to have those 3 values. If you don't have those 3 values, I can't do it.
Okay.
I'm a miracle worker, but not that much of a miracle worker. Alright, so let's plug this in. So in our calculator, we go 5, math, to the probability, NCR, 2. Then we times it by 0.51, raise it to the second power, times it by 0.49, raised to the third power. We hit enter, and voila, 0.3060. So the probability that this family has exactly 2 girls out of 5 kids is 0.3060. So we followed the same process for the next one. What number goes in here with x? 4. So now, 5 NCR, is it 2 here? What does this get replaced with? 4, because now I'm choosing 4 of them to be girls. So now it's 0.51 to the, you got it, 0.49 to the 1. These two numbers will always add up to your total. Now, calculator time. Math, whoops, sorry. 5, math. Probability, choose 4 times 0.51 raised to the 4th times 0.49. Do I have to say to the first? That's what I like at least about this one. I don't. 0.1657. I'm going to give you a 1-minute head start to do C.
Are we done after?
No, I still want to do the end of the bottom page and then the first half of the next. When she comes back, sure. To the fifth power, yeah. I choose, well, you're choosing, but none of them can be zeros, so this should be 0. Okay? So this would be if I choose 0. And then it would be, now you gotta flip your 0 and 5 around on the exponents. No, I apologize. Yeah, 0 and 5, that was actually right. It's just your CR, which was wrong. Well, it was given the same answer. That would have been just by here. Yep. Did you get 0.0282? Yeah.
Too good.
We're always gonna get X value.
I wish you would have gone to that one yet.
Did I do it wrong?
Because it's different. What does that say?
3.
Yeah, so that's exactly 3. So you've done at least the start of it. You'll have some space down here. All right, check up here. See how you did. Oh, sorry, me. So none of them girls. 5 choose 0. 0.51 to the 0 times 0.49 to the 5th power. Because none of them girls, all boys. Poor mom.
True.
True, right? My oldest cousin on my father's side he has 6 kids.
All
boys.
All girls.
The first 5 were all girls. And he wanted a boy so bad. His wife finally said, fine, one last child, but if it's not a boy, it's your fault. Okay? Which is true, because which gender actually determines?
Male.
The male does, because the male has the Y chromosome. Right? Because you have XX versus XY. So it's the male who determines the gender of the baby. And so he got lucky, yeah, he finally. I was a little bit worried for him because all of a sudden I'm just thinking to myself, I wonder if it's just genetic that you're always having, girls here. So he was lucky enough to have a
Do you have
boy.
a son or just one?
What's that?
Do you have a son?
I have a stepson, not a blood, not a
I thought
biological.
that Sophie
Mhm.
was your stepdaughter.
And Callie was my daughter, or?
We were just both really confused
Oh.
one day.
Because I thought you called Sophie your daughter one day and stepdaughter the other day. I was really confused.
I have a stepson, Danny, who's 20. I have a stepdaughter, Callie, who's 16.
Did she go here?
No, she goes to Holy Angels. So, yeah, I'm not. I don't like paying that bill.
Let's
Put it that way. Does she love her school? Is she getting a good education? Sure. Do I like paying for it? Do I think she could get just as good of education here? Yes.
And your daughter Sophie.
And then I have a daughter, Sophie, who's 5. So, and she, if I get my way, is to go here. So, if I'm still teaching here, that is. But,
Probability.
yeah. If we're fair to all the kids, we'll let her decide. So, because we let both Danny and Callie choose where they wanted to go to high school. Danny wanted to go here. So, all right. Anyway, notice how I've taken a little bit. I didn't ask you to do D yet, because what makes D totally different than ABC?
At least.
Oh, at least. So now all of a sudden I'm looking at what's the probability that X is at least, so greater than or equal to 3. So, one way I could do this problem is I could think of, well, at least 3 means X equals 3 plus X equals 4 plus X equals 5.
So much math.
Well, thank goodness I wasn't asking them to have 10 children and you had to do 3 or more. That's where the complement would come into play rather nicely. Because if you had to do 3 or more, you're better off doing 2 or less and subtracting from 1. Because you'd only have to calculate out 0, 1, and 2, add those 3 together and subtract from 1. But here it's kind of a tie. Have I done any of these probabilities? I did this one right here, didn't I? So 0.1657. So let's do this quick. Okay? Let's have this half of the room calculate out exactly 3. And let's have this half of the room do exactly 5, just to save a little bit of time. I'll write them both up here. If you don't know which one to do, pick one. It's okay. All right. Does someone have the 3? Taylor.
0.318.
Thank you. Does someone here have the 5? Really? No one has the 5?
Almost there.
Okay.
Got it ready.
Ben.
It's 0.0345.
Perfect. So now all I have to do is add these up, and I'm there. So let's do a quick 0.3184 plus 0.1657, 0.0345. It's gonna end in a 7, right? No, 6. Jeez. Come on, erase. Thank you. Ends in a 6, carry a 1. 12, 13, 18, carry a 1. Sorry, I'm just trying to add this in my head. Carry another 1. Is it 0.5186?
Yeah.
All right. So we got our probability. Woohoo! Now, you guys like this formula,
Yes.
Yes.
right? Some of you don't mind it. I actually don't mind doing it once in a while. Okay? I like breaking it out and using it. However, because technology is so unbelievably wonderful in your generation, okay? Your calculator has binomial calculations that you can do on your calculator. Okay? There's 2 of them that you can do that are very handy. They're noted right here. Okay? So, they are called binomial PDF and binomial CDF. In order to use these formulas, you have to know those 3 values, N, P, and K. Notice how both of them use them. So I think it was Asher that asked before, do you have to know these values in order to do it? Absolutely. Can't do it without it. Okay. Now, what's the difference between the 2? PDF just stands for a probability distribution. It's when you're doing an equals. So equals goes with the PDF. Okay. Binomial CDF is what's called the cumulative distribution function. Just like your normal curve and your table A, when you do normal distributions, the area is always at that score and everything less. That's how the binomial distribution works also with CDF. It will sum it at whatever number you want and everything less than that. So it'd be like 3 or less kids, or 2 or less kids, 5 or less kids, which would be them all, but it will do a specific number or less. So one of the things I could do, okay, is go up here and do these calculations doing binomial PDF and binomial CDF. So on this first one, so on the calc, okay, if I look at the first one here, I want to do binomial and use my calculator. Since it has the equals, I would go binomial PDF. Whoops, didn't finish binomial. PDF, and then I have to enter in the 3 numbers, which go N, P, K. So N is the number of total kids, my probability of a girl, how many girls I want, N, P, K. So if you use this formula and you write in these numbers, I want you to specifically tell me which number is N, which number is P, which number is K. So, how do I pop this up on my calculator? Okay. The directions are right there in your notes, and some of you have already read them, but it's in the same menu as normal PDF and CDF. So if I go second vars, there's normal PDF and CDF. You're probably going, wait a second, Bart, it's not there. But what you have to do is keep on scrolling, and if you scroll down, there's binomial PDF and CDF.
What's the difference between
Again, PDF is the equals, CDF is the less than. So CDF is cumulative, it sums a bunch of them together. So this one I want equals. So 5, comma, 0.51, comma, 2. So when I hit enter, notice how my answer is exactly the same as what I did when I used the formula. Okay? So like if I do this second one here, I go binomial PDF 5, comma, 0.51, comma, 4. Again, N, P, and K. I'm going to show you a little trick here. if I'm doing a lot of these PDFs, one of the things I can actually do is go second enter. It'll pull up the previous answer. I just changed this 2 to a 4. Notice how I get my answer to B to match up. Alright, let's look at C. Binomial PDF 5, comma, 0.51, comma, 0. Okay. So when I do this one, second enter, change that 4 to a, whoops, 0.
Correct.
So we're good. Now, the last one is the most challenging one because CDF is a less than statement. Is this a less than statement? No. However, all greater than statements can be written as a less than statement. Meaning, if I'm thinking about this, and I look at all the outcomes that are possibly being girls. 0, 1, 2, 3, 4, and 5. So these are the 6 different possibilities, and this is what I want. I want 3 through 5, don't I? Okay? What should all these possibilities add up to? 1. What is this? This is less than or equal to what? Not 3, but 2. It's 2, 1, and 0, so it's less than or equal to 2. I could use binomial CDF to get this value. If all of it adds to 1, if I take this value here and subtract from 1, I'll get 3, 4, 5. So this is the same thing as saying 1 minus the probability that x is less than or equal to 2. So now I can go 1 minus binomial CDF 5, comma, 0.51, comma, 2. So 1 minus second vars. I'm going to go to binomial CDF 5, comma, 0.51, comma, 2, close parentheses, hit enter. Notice how it's the same probability. We're off by 1/1000th there because of, or 1/10,000, because of rounding would be my guess. Alright, we will stop at this page and we'll continue on tomorrow with some more of the examples. I get that a lot.
If you want to stop.